See, here I am going to talk about parallel opposing connection, and here we are going to consider two inductors which are connected in parallel opposing fashion. I am going to find the equivalent inductance for the two inductors, okay, which is connected in parallel opposing connection. So before going into the derivation, let me explain how actually the self-induced voltage and mutually induced voltage are written. So for example, if I have an inductor like this, okay, so there is a current flowing through it, okay, there is a current flowing through the inductor, and there is some other inductor placed somewhere, there is another current flowing through that, okay. So if I consider the voltage across this particular inductor, there will be a self-induced voltage. The self-induced voltage will be due to the current I flowing through this inductor L1. Okay, so I will write that as L1 di by dt. This is self-induced voltage. Okay, so there will be two different voltages available in this inductor. There will be self-induced voltage and another one is mutually induced voltage. The mutually induced voltage is due to the current which is flowing through the nearby inductor, which is in close proximity. Due to that, okay, there will be flux lines generated by the inductor which will be linking the nearby inductor. Due to the current I2 flowing through the second inductor, which is L2, there will be voltage induced across L1. There will be voltage induced across L1. Okay, so I call that voltage as mutually induced voltage. Okay, the mutually induced voltage will be written like this: M di2 by dt. Okay, this is the voltage across this. Okay, M di2 by dt is the voltage across the L1 due to the current I2 flowing through L2. Okay, so if I consider an inductor, there will be two different voltages. One is self-induced voltage and second one is mutually induced voltage. The self-induced voltage will be written using the inductance value, okay, and then current flowing through that with respect to the time, L1 di by dt, which I call it as what? Self-induced voltage. Okay, another case is mutually induced voltage, that is due to the another current, okay, which is flowing through a nearby inductor. Okay, the current which is flowing through a nearby inductor, which will generate the voltage across the first inductor, which is L1. Okay, so in this case, in our example, I2 is the current flowing through L2. Due to the current I2 flowing through L2, there is a induced voltage across L1. There is an induced voltage across L1, that I call it as mutually induced voltage. That will be represented like this. M is a mutual inductance. Here L1 is self-inductance. M is a mutual inductance, di2 by dt. Okay, di2 by dt. Okay, that is due to the current I2. It can be any current. It can be any current. Okay. Okay, now let us start the derivation. So just give me a time. I'll just erase all these things. Okay, I hope it is sufficient. Okay, let us start. Okay, it is very similar to what we discussed in parallel aiding connection, but the place of dot is in different places. Okay, that we need to consider for positive and negative signs. Okay, so we are supposed to follow the dot convention. Okay, I'll provide a new video for dot convention separately. So if you didn't understand how I mentioned the polarities, just watch that video. Okay, so now come to the parallel opposing connection. Let us take the loop. Yeah, loop 1. Okay, loop 1. So I am just considering the clockwise direction, so minus V, because the current entering negative, leaving positive. Okay, and then there is a self-induced voltage across it. Okay, so L1 di1 by dt, because I1 is the current entering this L1. Self-induced voltage will be due to the current flowing through the L1. Okay, so L1 di1 by dt. Okay, and then I have written minus M di2 by dt. So that is due to the current I2. The current I2 is entering the undotted terminal. So the generated mutual voltage across the L1, positive will be here and negative will be here. Okay, this is the generated mutual induced voltage polarity based on the dot convention. Okay, based on the dot convention. The dot convention says that the current enters the undotted terminal. The generated voltage in the nearby coil, positive polarity, will be at the undotted terminal. Okay, so if I consider the clockwise direction, the clockwise direction current is entering negative, leaving positive. So it does not obey the passive sign convention, so I am writing minus. Okay, what is the mutual induced voltage? I will write M. It was due to the current I2, so dI2 with respect to the time. So minus, okay, because it is not obeying the passive sign convention, M dI2 by dt equal to 0. So I can rearrange it, V equal to L1 dI1 by dt minus M dI2 by dt, which is equation 1. Okay, similarly I need to apply KVL at loop 2. So while applying KVL at loop 2, I need to consider voltage V across this, because all the three elements are parallel. L1 and L2 are parallel. Across that we have a voltage V. I am giving the same polarity what I mentioned here across L1. Okay, so I am applying KVL. So here also the current entering negative, leaving positive, so minus V, plus there is a self-induced voltage across this, which is L2 dI2 by dt. Okay, this is self-induced voltage, self-induced. The second one is mutually induced. Okay, second one is mutually induced. I will just erase. Okay. Now the mutually induced voltage across this L2 will be due to the current flowing through the L1. Okay, the current is entering the dot. Okay, current is entering the dot. So the induced voltage in the L2, positive will be at the dotted terminal and negative will be at the undotted terminal. The current is entering the dot, so the generated voltage positive will be at the dot, the negative will be at the undotted. So while checking the current direction, the current is entering the negative terminal and leaving the positive. So it does not obey the passive sign convention. Okay, so what is the mutual voltage? So I can write M. It is due to the current I1, so dI1 by dt. So this is the mutually induced voltage across L2. Okay, so it does not obey passive sign convention, so minus sign is written. So M d I1 by dt, because it is due to the current I1 flowing through L1, equal to 0. So I can write V equal to L2 dI2 by dt minus M dI1 by dt, which is equation number 2. Okay. Next I am going to consider the node A, applying KCL at node A. I is the current entering, so plus I, minus I1, minus I2, because I1 and I2 are leaving. So I minus I1 minus I2. Okay. So that can be rearranged like this, I equal to I1 plus I2. I am going to differentiate this with respect to time for on both sides. So I can be written as di by dt, I1 can be written as di1 by dt, I2 can be written as di2 by dt. Okay. So now I am going to write this two different equations, one for di1 by dt and another one for di2 by dt. Okay, simply rearranging. So di1 by dt means this di2 by dt will be going to the left hand side. Next, if you want to find out di2 by dt, di1 by dt should be going to the left hand side. So di1 by dt will be written as di by dt minus di2 by dt. So di2 by dt can be written as di by dt minus di1 by dt. Okay, similar to what we discussed in parallel aiding connection. So now I need to substitute this equation 3 or equation 4, okay, in the equation 5. First of all, how do we get this equation 5? So we have written the equation 1 and 2, right? So just check the left hand side of equation 1 and 2, it is V. Okay, same for both the equation, the left hand side is same. So I can equate equation 1 and equation 2. Okay, so what I will get? L1 di1 by dt minus M di2 by dt equal to L2 di2 by dt minus M di1 by dt. Okay, so I equated the equation 1 and equation 2. Okay, I have written it as equation number 5. Now I have to substitute these equations one by one. Okay, first let me substitute equation 4 in 5. The equation 4 is substituted in 5. So all the di2 by dt will be replaced by this di by dt minus di1 by dt. Okay, so this di2 by dt will be replaced by di by dt minus di1 by dt, and this di2 by dt will be replaced by di1 by dt by di1 by dt. Okay, so next I am going to rearrange this. I am going to take all the di1 by dt to one side and all the di by dt to other side. Okay, so by rearranging I am going to get all the di1 by dt here on the left hand side. So L1 di1 by dt, m di1 by dt plus L2 di1 by dt plus m di1 by dt equal to, okay, all the di by dt on the right hand side. Whatever equation we got here, I am just rearranging by placing all the di1 by dt on the left and all the di by dt on the right. And I have taken di1 by dt outside. I got L1 plus L2 plus 2m. Here I have taken di by dt out. So I will get L2 plus m into di by dt. So di1 by dt can be written as, this can be taken to the numerator. So L2 plus m by L1 plus L2 plus 2m di by dt. Equation number 6. The next step is I need to substitute this equation number 3 in this equation. If I want to substitute equation number 3 in this, wherever you find di1 by dt, I have to substitute the right hand side value. Okay. So that is what I have done here. I need to do the same step what we discussed here. I need to arrange all the di2 by dt on one side and all the di by dt on the other side. So while doing that, I will be getting the equation like this. So di2 by dt equal to L1 plus m by L1 plus L2 plus 2m into di by dt. So this is what we get. Okay, now we have di1 by dt in equation number 6 and di2 by dt in equation number 7. Okay, now we need to substitute this equation 6 and 7 in equation number 1. Okay, so we got the equation like v equal to L1 L2 plus m by L1 plus L2 plus 2m into di by dt minus m into L1 plus m by L1 plus L2 plus 2m into di by dt. Okay, I can take this L1 inside, here I can take this m inside, and I can take this di by dt outside because it is common. I got L1 L2 plus L1m by denominator same minus m can be taken in, it is minus m. Okay, so be careful while taking it. Okay, so I am keeping it minus outside and taking m only inside. So m L1 plus m square by denominator will be same. Okay, now take the minus inside. So minus m L1 minus m square by all these things. So I can cancel this 2. I will get L1 L2 minus m square by L1 plus L2 plus 2m into di by dt. So I am comparing with this equivalent circuit. This is the equivalent circuit. If I have multiple inductors, if I find the equivalent inductance, I will be drawing like this, L equivalent. If I want to write the voltage across this, it will be written as V equal to L equivalent di by dt. Instead of L equivalent, what we have, just compare these two equations. Instead of L equivalent, what we have here, L1 L2 minus m square by L1 plus L2 plus 2m. So that is the L equivalent formula for parallel opposing connection. Okay. If you have any doubts, kindly put it in the chat. Okay. Thank you.